Okay, so what we're going to do now is going into investigation 3, we're going to relate position graphs and velocity graphs to each other. Now, since it makes sense that if you do certain motion, you can get a position versus time graph. If you do the same motion, you can get a velocity versus time graph. So is it possible? So let's see if we can see the relationship and be able to predict one to the other. That is to say, if you get a position graph, can you get a velocity graph? If you have a velocity graph, can you get a position graph? Okay? So activity 3-1, predicting velocity graphs from position graphs. What I want you to do is first, I want you to predict what the velocity graph is going to look like given this position graph. Okay, so as you can see, the position graph starts at just beyond 1 meter, or 0 meters, and then for 3 seconds moves away to 3 meters, and then stays at 3 meters. So what would the velocity graph look like for that motion? Okay, I'll let you do that, and then just for the sake of time, what I'm going to do is I'm going to go ahead and do the motion. So I'll position myself here. There's the record button right there. Okay. This thing you see here, I'll show you how that works in a bit. So let me turn that off. Okay, now let me change this velocity graph. The color on the velocity graph is kind of hard to see, isn't it? Especially for those of you in the back. So let's go ahead and just do that. That makes it a little easier to see. Okay? All good? All right. So we go down to question 3.1. Well, first of all, did it match the prediction? Does your graph look like the graph that I made? Okay. Not at all? Okay. Well, as you can see, first of all, does my position graph somewhat match the position graph in the diagram? Okay. So therefore, would this kind of match? Actually, that was really close. A little closer than I expected. A little off by half a second. So does the velocity graph match what you predicted? You should have gotten a constant velocity in the positive direction. And in fact, given that you're starting at 0 and going to 3 meters in about 2.5 seconds, then 3 meters divided by 2.5 seconds gives you, just under a meter, like 0.8 meters per second or something like that. So your velocity graph should be straight across at about 0.8 meters per second, and then you come to a stop when it comes to 0. Make sense? Okay. Now, question 3-1. How would the position graph be different if I had traveled faster? What would the position graph look like if I traveled faster? Yes? The slope would have been greater, correct? And what would have happened if I had traveled slower? 3-2. Yes? I saw a hand back there. Did you want to give it a go? What would the position graph, the top graph, look like if I had traveled slower? Go ahead. The position, the top graph. What would this graph look like if I traveled slower than this? The slope would be less. Very good. Exactly right. Okay. Now, how would the velocity graphs be different? Well, the velocity graphs are real straightforward. If I'm going faster, it would be higher. If I'm going slower, it'd be lower. Okay. Now, we go to activity 3-2, calculating the average velocity. So what I'm going to do is I'm going to use my computer to get data to calculate what the average velocity of the motion is. And on page 16, we have a table of velocity values. So I'm going to go ahead and jot those down. Okay, so here's my velocity values. And I'm going to go ahead and select 10 velocities at random. So as you can see, I'm going to use this slider here to get the 10 velocities. So let's just start off at this point right here. And the first one is 0.57. Then I'm going to go to 0.81. 0.67. 0.74. 0.74, that's 5 data points. 0.69, and I'm writing these down too so you can copy them onto your table. 0.77, 0.62, 0.74, and the last data point will be, call it 0.59. Okay? So there's the table of the data. Now, what is the mean of that velocity? What is the mean of all those velocities? What is the average of those velocities? Mm-hmm. Okay, so what do we got? Yes? So we got an average V bar of 0.69. Anybody else? Does that agree with what you guys come up with? Okay, so that's what we will put down as the average of the velocity. That's on page 16. Question, now, in the comment, in the comment here, average velocity during a particular time interval can also be calculated as the change in position divided by the change in time. The change in position is often called the displacement. For motion with a constant velocity, this is also the shape of the, For motion with a constant velocity, this is also the slope of the position time graph for that time period. As you've observed, the faster you move, the steeper your position time graph becomes. The slope is a quantitative measure of this incline. The size of this number tells you the speed, and the sign tells you the direction. Let's go ahead and calculate the slope then. What I'm going to do is I'm going to choose 2 data points. All right, so I'm going to choose 2 data points. The first data point will be all the way over here. Again, this is going to be random. We're looking at a position. The x position is 0.55 meters, and the time is going to be 0.150 seconds. So this is meters, and this is seconds. Then I'm going to go all the way over here, and I'll just choose that point there. The position is 2.67 meters, and the time is 3.20 seconds. All right, now we need to find the change in position. The change in position turns out to be 2.12 meters, and the change in time turns out to be 3.050 seconds. Yes? Sure, on those. There we go. So this is the change, what I refer to as the delta, okay? As you can see, what I did was I took the bottom one, subtracted the top one from it. All good so far? Does my math match your math? Don't take my word for it. I gave you the numbers. You should be able to figure out the same things. Okay? Now, the next thing we need to find out is what is the average velocity. The average velocity turns out to be the change in the x divided by the change in the time, or in this case, 2.12 meters divided by 3.05 seconds. So what's that number? Yes? 0.70 meters per second. 0.70 meters per second. Again, do the math yourself. I gave you the numbers. You should be able to do the math to confirm that. Okay? Now, that leads us then to the next question, question 3-3, which is the average velocity positive or negative? All right, is the average velocity positive or negative? What is it? It's positive. We saw that the position increased over time, which gave us a positive slope. Is this what you expected? Okay, because it did match the fact that we had a positive velocity on a velocity graph, yes? Now, question 3-4. Does the average velocity you just calculated from the position graph agree with the average velocity you found in the velocity graph? The velocity graph, we came up with 0.69 meters per second. The position graph, we came up with 0.70 meters per second. Is that a good agreement? Is that close enough agreement? Especially considering the fact when we did the three significant figures, we got 0.695. So yeah, that's very, very good agreement. Okay, do you expect them to agree? And how would you account for any differences? Why would there be some difference? Here's one. Did I use all the data points for the velocity? I picked 10 velocity, right? What if I picked a different set of 10? I probably would be close, but could I get the same number? More or less, but may not necessarily be the same, the last digit may be different. Okay? Now, I'm going to go ahead and do the extension here, 3-3, because here's the cool thing. We can do this stuff mechanically. We can do this stuff by hand. But computers are certainly programmed to do stuff like this as well. So let's take advantage of the computers. All right? It turns out that the computer has statistics functions, or the software has statistics functions that I can take advantage of. So I'm going to turn this off. And here's what we're going to do. First, question 3, using statistics, you must first select the portion of the velocity time graph that you want to find the mean value. So I want to find the average of the velocities. So what I'm going to do is I'm going to use this tool, highlighter tool. So I click on the velocity graph. I click on the highlighter tool, and you can see I get a highlighting box. And that highlighting box allows me to highlight all the data for that particular motion. So I'm going to highlight the data up to about 3.4 seconds. Next, I need to find the mean of this. Well, I have a button right here, which is my statistics button, the one that looks like the Greek letter sigma. When I click on the pull-down menu, I see I can get the minimum, the maximum, the mean, the standard deviation, a count of the data, and I can make a table. Now, since mean is already selected, all I've got to do is push the sigma button, and the mean turns out to be 0.68 meters per second. Of course, if I slide it over a little bit like this, 0.69 meters per second. This little outlier right here could be dragging it down. Okay? So I'm going to leave it like that at 0.69. Not bad, yes? Let the computer do the work for you. You know the reason why. Now we can let the computer do the work. What about for the position graph? Well, for the position graph, we want to use a fit. So what we need to do is we need to select the data where I was moving. So let's use the exact same time interval. I'll click on the position graph. I'll click on the highlighter. And now I will highlight the data for the same time interval, 3.4, 3.3 seconds. Okay? Now what I'm going to do is I'm going to click on this button here. Now this button here is a curve fit function. When I click on it, that gives me a list of functions that I could try to fit to the data selected. So if my functions are going up and down, if my data is going up and down, I could see if a sine curve fits. Or if it's got an arch, maybe a parabola or a cubic or an exponential. Do you see where we're going here? Let the computer do all the hard work for you, right? In this particular case, it looks like a straight line, so I've got linear selected. So all I got to do is push the button to activate it. There's the line. The line has a slope of 0.696 meters per second. It has a y-intercept of 0.464 meters. What does that y-intercept b mean physically? Yeah, but what does it mean physically? Where I began. Yes, at time zero, where this data, at time zero, where was I standing? I was standing about the half-meter mark. Okay? So that's question E3-6. What is the meaning of B? B is where I was standing at time zero. And E7, do the two values of velocity that you found here agree with each other? We got 0.69 on the average of the velocities, and we got 0.696 for the slope of the position graph. Do those agree? Yes, they do. Very well. Is this what you expected? The answer is, well, it's certainly what I expected. Yes. Okay. Now we're going to do one more of these matching graphs here. You see, what we did was we predicted the velocity from the position graph. Now I want you to predict the position from the velocity graph. So given the velocity graph here, what is the position graph going to look like? Okay? Given that velocity graph, what does the position graph look like? All right, so draw your prediction on the prediction graph on page 18. Oh, by the way, can we get... So as you can see, the bottom of it says we're going to start at 1 meter. What kind of motion? I'm going to go ahead and make the motion. What kind of motion should I have for the first 3 seconds? Stand still. So where am I going to be for the first 3 seconds? At 1 meter. Then what am I going to do from 3 to 6 seconds? Okay, how fast? Half a meter per second. All you got to do is read it right on the scale right there. Half a meter per second. Where am I going to end up? No, where, not when. Where am I going to end up at the end of 6 seconds? 3 meters away. How do you know I'm going to be 3 meters away? 0.5 times what? No, not 6. 3. So I'm only going to be 1.5 meters as to how far I'm going to travel. See, when you look at this, you're not looking at this time right here. You're looking at this time right here. That's the time I'm actually moving. You see? In fact, what you're looking for is trying to figure out what the area of this block is. And what is the area of this block? What's the base times the height going to give me? What's the number? 1.5 here. What's the area of this block? Okay, but what's the sign going to be? Negative, because it's below the 0 line. So I'm going to go away 1.5 meters. I should come back 1.5 meters, which means where do I end up? I should end up not at 0, where I started. My overall change in position should be 0. Does that make sense now, guys? Okay, so why don't I go ahead and do that? So I'm going to go ahead and stand at the 1 meter mark, and I'm going to walk backwards about 1.5 meters over 3 seconds. So this is about, let's see, that's 2 meters, so that would be right about here, okay? So I got to stand still for 3 seconds. and then I got to walk backwards for 6, and then walk forwards, and I screwed it up. But, so I'm going to give it another go. Why not, So, yeah, because I was looking at the velocity, not the position graph. Okay. Well, could have been better, but close enough for government work, so to speak. So does the position graph, okay, first of all, does this velocity graph here pretty much match this velocity graph here? Yes, it does. So therefore, does this position graph here match your prediction for what your position graph was? Okay. Question 3-8, how can you tell from a velocity time graph that the moving object has changed direction? How can you tell looking at this graph down here that I've changed direction? Yes? Went from positive to negative, exactly right. Here it's positive velocity, which means I'm moving away. Here's negative velocity, which means I'm moving toward. So when it crosses over the line on the velocity graph, I have to change directions. Exactly right, very good. Question number 3, what is the velocity at the moment that the direction changes? It's 0, exactly right. Okay, and now question 3-9, how can you tell from the position graph that your motion is steady? How can you tell from this graph that I'm moving at a constant speed or a constant velocity? Yes? This is a straight line. Here I have a straight line at 0. Here I have a straight line with a slope. Here I have another straight line with a slope and another straight line at 0. So we can get a lot of information from these graphs here. Okay, I'm going to set up one more experiment. It's going to take 5 minutes to do, not the setup, but the experiment itself. So all I need to do is grab this, and we will do investigation 4. Now, investigation 4 requires that I change. And by the way, 3:10, how can you tell from the velocity time graph that your motion is steady or at a constant velocity? Because it's a straight line going across. Yes, very good. Okay, so let me set up my equipment here. All right. And, oh, wait a minute, I do need to change things. Okay. Well, I'm not going to bother changing it, so we'll just have to do it the hard way. Okay. Okay, what do we got to do here? Okay. So investigation 4 is an introduction to acceleration. There's a third quantity besides position and velocity that's used to describe the motion of an object called acceleration. The acceleration is defined as the rate change of velocity with respect to time, just like velocity is defined as the rate change of position with respect to time. In this investigation, you'll begin to examine the acceleration. Because of the jerky nature of motion of your body, the acceleration graphs are very complex. It'll be easier to examine the motion of a cart. In this investigation, you'll examine the cart moving with a constant, steady velocity. So I'm going to need to change my camera controls a little bit. Let's see, will that work for me? No, that won't work for me. So let's do that. All right. So there we go. I know, you can kind of, and let's just do a little bit over here. All right, so now you can see this cart here is what's going to be moving. All right. So what we're going to do is, I'm going to have a little tough time of this. Oh, wow, I didn't want to do that. I want to do, let's leave this here. So we've got it set up, prediction 1-4. How should the position and time graphs, position and velocity graphs look if you move a cart at a constant velocity away from the motion detector starting close to the motion sensor? So I'm going to put the cart all the way over here. I'm going to give it a push and let it coast, hopefully at a constant speed. Okay, what should the position and velocity graphs look like? Okay. While you're making your predictions, I'm going to do a quick little thing. What I'm doing is I'm putting in a start condition and a stop condition so that the computer will turn it on and turn it off, the data recording, automatically. Oops. Okay. All right, so what should the velocity graph look like? What do you think it'll look like? If it's moving at a constant speed in this direction, what should it look like? It should look like a straight line. What should the position graph look like? Constant slope increasing, okay? So let's go ahead and do the experiment. Make sure you put your predictions on, page 20, okay? So here we got it set up. And let's see if, perfect. Oh, don't worry. It looks weird because of the time scale. So let's increase the time scale, and now it makes a little bit more sense, doesn't it? Okay? So, looking at this graph right here, from about 0.2 of a second forward is when we got good data. Okay? So does this position graph match your predicted position graph? I should see a lot of heads going up and down. Does your velocity graph match your velocity graph? For the most part, yes. There is a slight downward turn, but it's not that bad. Okay? Question 4-1, did your position, time, and velocity time graphs agree with your predictions? What characterized constant velocity and position time graph? We already talked about that. And what characterizes constant velocity on the velocity time graph? Now, activity 4-2 is what does the acceleration look like? So in activity 4-2, what I'm going to do, well, the good news is I don't have to do much of anything. What I'm going to do, there we go. So what does the acceleration look like? Now, how do I find the acceleration? Sketch with a dashed line on the axes that follow your prediction of the acceleration of the cart you just observed moving at a constant velocity. So, is the velocity changing? No, it is not. So what should the acceleration be then? Should be 0. So what should your acceleration time graph look like then? Should look like a straight line. Where? On 0. So I'm going to go ahead and change that position graph to show an acceleration graph. There's my acceleration graph. Again, ignore everything before the 0.2 seconds. Let's look at this. So do you see the acceleration graph? It may be kind of hard to see, so let me go ahead and change the color, make it a little bit darker to see. Actually, let's make it a nice bright red. All right, now you can see it, yes? Okay, so look at that acceleration graph. What does it look like? Does that match your prediction? Okay, so as you can see, it's 0 there. Now, question 4-3, does the acceleration time graph you observed agree with the method of calculating acceleration? And the answer is yes. So, because in the comment it says if you use the slope of the velocity graph, you can find the acceleration. 2 more questions. The diagram below shows the positions of the cart at equal time intervals. At each indicated time, sketch a vector above the cart that represents the velocity of the cart at the time it's moving at a constant velocity away from the motion detector. So, is the velocity changing at each time? Is the velocity at each time the same, or are they different? So what should the vectors look like at each time? They should be the same length pointing in the same direction. So at every point above the cart, you draw an arrow pointing to the right, And all of those arrows are going to be the same length. To find the average acceleration, you must find the velocity, the vector that represents the change in the velocity. So how would we represent the change in the velocity? Well, that's easy to do. If we have this arrow represent, say, a velocity at time 1, and this arrow represents the velocity at time 2, then what is the difference between these two arrows? What do I have to do to go from the head of this arrow to the head of this arrow? Well, no, there is no, well, I'm just stacking them one on top of another. As far as the lengths are concerned, they're the same length, right? So therefore, this line right here, it's the same length. The change in the velocity, delta v, would be 0. Does that make sense now, guys? Let me give you another example. If I had an arrow this way, this is v1, and I had another arrow here, this is v2, then how do I get from this arrow to this arrow? Well, then I have to add that velocity on top of it, and that's a delta v. Does that make sense now? Okay, so now you see why we don't have to add another arrow, because each of those velocities at each of those times are the same. So the acceleration happened to be 0 for the overall. And that finishes it. 5 minutes left to go in the period. Thank you very much for your patience. I've got to check these to see whether or not they're recording properly. If they did record properly, I should have them on the YouTube channel this afternoon if you want to review them. If you have any questions, come see me. The WebAssign is active for this particular exam, for this lab. All right, that's all I got.